All right, let's dive into one of the weirdest, most mind-bending ideas in all of physics. It's this idea that everything, everything, from a ray of light to, well, you and me, is living a kind of secret double life.
Now, to really wrap our heads around this, you gotta go back in time. We're talking the late 1800s, and physicists back then, man, they were feeling really good about things. They pretty much thought they had the universe all figured out.
And the one thing they were absolutely sure of? Light. Thanks to Maxwell's equations and some brilliant experiments by Hertz in '87, it was case closed. Light was a wave. End of story. It did all the wave stuff. It could interfere, diffract, you name it. Classic wave behavior.
But here's the kicker. What if, hiding in plain sight, right there in the sparks of one of those very experiments, was a tiny clue that was about to blow everything they thought they knew wide open?
And that brings us to this phenomenon that, it started off as just a little weird observation, but it ended up kicking off a whole revolution in physics.
So get this, it's 1887, and Heinrich Hertz, the same guy who just proved light was a wave, he notices something kind of odd. He's working with his setup, and when he shines some ultraviolet light on a metal plate, the sparks just jump easier. The light was literally helping electricity to flow. How strange is that?
So other scientists, folks like Hallwachs and Lenard, they jumped all over this. And they figured it out. The light was knocking these little negative particles, we call them electrons now, right off the metal. They gave it a name, the photoelectric effect. Makes sense, right? Photo for light, electric for the electrons. But oh boy, the details were about to get messy.
Because once they started measuring this thing really carefully, the results just made no sense at all. That trusted, proven wave theory of light, it just completely and totally fell apart.
So first mystery up was the intensity puzzle. Now, if light's a wave, then brighter light is a bigger, more powerful wave, right? So logically, it should smack the electrons harder and send them flying off way faster. Makes sense.
Yeah, well, the experimental reality was a big fat no. Sure, brighter light knocked out more electrons. You'd get a bigger current. But the speed? The top speed of those electrons was exactly the same, whether the light was dim or blindingly bright. And wave theory? It had absolutely no answer for that.
Okay, so just look at the actual data here. The way they measured this was pretty clever. They'd see how much voltage they needed to apply to stop the electrons in their tracks. They called it the stopping potential, and it's basically just a way to measure the electron's maximum energy. And what you see on this graph is crazy. You've got different light intensities, I1, I2, I3, and yet that stopping potential, V0, it doesn't budge, not one bit. This was the smoking gun. Brightness had nothing to do with the energy.
All right, so if the brightness doesn't change the electron's energy, then what does? That led them to the next big puzzle. What about the color of the light? Its frequency.
And this part was just totally bizarre. A low-frequency red light might not do anything at all, but a high-frequency blue or UV light would send those electrons shooting out. And the higher the light's frequency, the more energy the electrons had. Once again, the wave model just had nothing. It was completely stumped.
The wave theory would suggest that, look, if you just make any light wave intense enough, like a giant ocean wave, it should eventually build up enough energy to push an electron out. So could a really, really bright red light get the job done eventually? Nope, not a chance. The experiments showed this really strict rule. Every metal has something called a threshold frequency. If your light's frequency is below that specific cutoff, you can make it as bright as the sun and shine it for 1,000,000 years, and not one single electron is going to pop out. It was a total all or nothing situation. And that brings us to the final nail in the coffin. If light is a continuous wave slowly washing over the metal, an electron would need some time to absorb enough energy to escape, wouldn't it? Especially if the light was pretty dim.
The math, based on wave theory, said it could take hours for an electron to get enough energy. But what really happened, it was instant. The second that light hit the metal, electrons were flying off. We're talking less than a billionth of a second. This was it. This was the final, fatal blow. The wave theory just couldn't explain this.
So for years, these puzzles just confused the heck out of the smartest physicists on the planet. And then in 1905, this young patent clerk, a guy named Albert Einstein, he comes along with an idea so wild, so out there, it was going to change science forever.
He basically said, forget the smooth, continuous wave.
What if light energy isn't spread out, but comes in these little, discrete bullets of energy? He called them quanta. Think of it this way. Light energy isn't a smooth ramp. It's a staircase. You can only be on one step or another, nothing in between.
And he put this whole thing into one beautiful, simple little equation. All it says is that the max energy of the electron is just the energy of one of these light packets, minus something called the work function. You can think of that work function like a cover charge at a club. It's the bare minimum energy the electron needs to pay just to get out the door.
And just like that, with this one idea, everything clicked. All those crazy puzzles, they just vanished. Why doesn't brightness matter? Because more brightness just means more packets, not stronger ones. Why does color matter? Easy. The packet's energy is tied directly to its frequency. That threshold thing makes perfect sense now. A single packet has to have enough juice to pay that escape fee. And the time delay? Gone. It's not a slow soak, it's a one-on-one collision. One packet hits one electron. Bam, done. It was just so simple, so elegant, and it solved everything. Now, Einstein's idea was, well, it was revolutionary. And like most revolutionary ideas, it took a while for people to come around. It needed some solid proof.
And here's the best part. This physicist, R.A. Millikan, he thought Einstein was totally wrong. So he spent 10 years in his lab doing these incredibly careful experiments just to disprove the whole idea. And the result? In 1916, he ended up proving Einstein was perfectly right. I love that. And you know, it was this work, not relativity, that actually won Einstein his Nobel Prize. A little later, these light quanta got the cool name we all know today, photons.
Okay, so the physics world had to swallow this crazy new pill. Light, which they thought of as pure energy, could act just like a tiny particle. This discovery just blew up the old lines between waves and particles. But, you know, once you start messing with lines like that, it makes you ask an even crazier question. What about the other side of things? What about matter? So in 1924, this French physicist, Louis de Broglie, he has this really simple, almost poetic thought. He says, hey, if waves can be particles, why can't particles, like electrons, be waves? He just figured nature ought to be symmetrical, that both energy and matter should have this weird dual personality.
De Broglie even came up with an equation for it. So why don't we see a baseball kind of waving as it flies past? Well, just look at the comparison here. The wavelength of a baseball is so ridiculously, impossibly tiny that there's no way we could ever detect it. But for a little electron, its wavelength is totally measurable, about the same as an X-ray. And sure enough, when they shot electrons through a crystal, they saw an interference pattern, which was 100% wave behavior. De Broglie was right.
So here's the takeaway, the really big idea. Everything has this dual nature. Light isn't sometimes a wave and sometimes a particle. It's somehow both, all the time. And it's not just light. It's electrons, it's atoms, it's you. So that leaves us with a pretty deep question to chew on, doesn't it? If the absolute fundamental building blocks of our universe refuse to be pinned down to being just one thing, what does it even mean to be real?